The purpose of these next two sections, 11.1 and 11.2, is introduce a more general way of describing curves in the plane. The method can be very useful for describing the motion of an object, but it too lets us study curves more general than what we've seen until now. In particular, curves don't need to be the graph of a single function. To show how this works, consider the following example. You'll see in example 1, the curve is described using two functions, x is equal to t minus 1, and y is t cubed plus 1. The parameter interval is -2 to 2, and the parameter t won't show up directly in our graph. To demonstrate how this curve works, I'll make a table for some well-chosen values of t in the parameter interval. Let's say t takes values -2, -1, 0, 1, and 2. And plugging into the formula for x, we'll see the corresponding x are -3, -2, -1, 0, and 1. Meanwhile, the y values are -7, 0, 1, 1 cubed plus 1 is 2, and 2 cubed plus 1 is 9. I'll then go ahead and plot points. I'll still have x-axis, y-axis, and I'll plot the corresponding pairs -3, -7, -2, 0, -1, 1, 0, 2, and 1, 9. Okay, and I can go ahead and connect them up. Here, the smallest value of t corresponds with the initial point of the curve, and the largest value of t, that is t equal 2, that's called the terminal point. And convention is to also indicate with an arrow the direction of increasing t. That's also called the direction of the curve. Sometimes thought that t is the time parameter. For the second part is to make the connection between parametrized curves and curves as we've seen them before. So to eliminate the parameter, it's here possible to solve one of the defining equations for t. So here, I think we can solve one for t. So that gives that t equals x plus 1. And then substitute into 2 to get that y equals x plus 1 cubed plus 1. And so that's an equation with the Cartesian x and y, but t is gone. So we see that our curve also is the graph of this cubic equation.